In our previous units, we explored fundamental machine learning algorithms like decision trees or regression. Now we introduce ensemble learning, a method where multiple models are trained and their predictions are combined to enhance robustness and accuracy. You will see that a team of weak learners can be much stronger than a single strong learner. The method of ensemble learning involves the training of multiple small models whose predictions are combined to yield a more accurate outcome. The general principle of ensemble learning can be divided into two families, bagging and boosting. Let's first learn the general principles of the bagging approach. Bagging, or bootstrap aggregating, operates by creating multiple training datasets through bootstrapping. Bootstrapping involves randomly selecting samples from the original data, but with replacement. This means that some values may appear multiple times in a single sample. These samples are then used to train individual models in parallel, each model learning independently from its own dataset. Now let's take a closer look at random forest, a prominent example of bagging in action. Each tree is trained on a random subset of attributes and a subset of the data rows from the original dataset. By creating diverse trees with reduced correlation, random forest decreases overall error. Typically comprising around 100 or more trees, the forest uses a majority vote mechanism for prediction in classification problems and averages predictions in regression. This approach prevents overfitting and maintains strong performance even with large datasets. Boosting, on the other hand, operates sequentially. In boosting, models are trained iteratively, with each subsequent model focusing on correcting the errors made by its predecessors. Initially, all data points are given equal weight, but as iterations progresses, more weight is assigned to misclassified data points, effectively prioritizing the learning of challenging instances. Gradient-boosted decision tree is an example for boosting. This method iteratively refines models by focusing on the correction of errors from previous iterations. While yielding impressive accuracy, the sequential nature of boosted trees demands vigilant management to prevent overfitting. As with many other machine learning methods, tuning hyperparameters is a critical step in maximizing model performance. From the number of models to the learning rate, each parameter significantly influences the model's predictive power. However, identifying the optimal configuration defines finesse and often relies on tricky experimentation with so-called validation datasets. In conclusion, ensemble methods like bagging and boosting offer powerful tools to enhance machine learning models' accuracy and robustness. By leveraging the collective intelligence of multiple models, we can mitigate overfitting and improve predictive performance. But to realize the full potential of these methods, don't forget to carefully tune the hyperparameters.